Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on June 26, 2025. This paper, published just 2 days ago, introduces a new method to monitor model training that shows a stunning correlation with test accuracy of over 0.97, all without using a test set. The paper is titled, Where to Find Grokking in LLM Pretraining, Monitor Memorization-to-Generalization Without Test. And the implications for how we train these giant models are pretty significant. It focuses on a phenomenon called grokking, which is when a model's performance keeps improving long after its training loss has flatlined. Alright, so to dig into this, let's look at the first figure. The model studied here is a mixture of experts, which is like having a team of specialized mini-models, or experts, inside a larger one. The model learns to route each task to the most relevant experts. These charts show that the point where test accuracy rises sharply, what they call the global grokking point, happens at different times for each data domain, like math or code. This shows grokking isn't one single event, but happens locally for different types of data. Building on that idea, these charts really visualize this local grokking. We see 4 plots here, each for a different group of data. In every case, the training loss, that's the blue line, flattens out very early on. But the test accuracy, the red line, stays low for a long time before suddenly shooting up. This delay, the grokking phase, gets systematically longer for the harder data groups. This really drives home that training loss is a poor guide for when the model is actually generalizing its knowledge effectively. So if training loss isn't a reliable guide, what is? Well, to get at the mechanism behind grokking, the authors developed 2 new metrics. The first, on the left, is called pathway distance. It measures how similar the paths through the model's experts are for different pieces of data. A lower distance suggests the model is creating more structured, shared routes. The second metric, on the right, is pathway consistency. This one looks at a single path and measures how smoothly information flows between layers. Basically, how coherent the expert choices are. So these next plots really show the power of that pathway distance metric. We're looking at 4 domains here: math, code, common sense, and domain specific. In every single chart, you can see the training loss. Those dotted lines flatten out very early, but the solid lines, which represent the pathway distance, keep going down. This distance is measured using something called edit distance, which basically counts the differences between 2 expert pathways. The fact that this distance keeps dropping shows the model is actively reorganizing its knowledge into more efficient, shared structures. And this table really puts some hard numbers to that observation. It shows the correlation, which is a statistical measure of how 2 things are related, between these new pathway metrics and the final test accuracy. Look at the top 2 rows. Pathway distance has a strong negative correlation, around negative 0.95. This means as the pathways become more similar, their distance drops, the test accuracy reliably goes up, and pathway consistency shows an even stronger positive correlation, often above 0.97. In contrast, the loss metrics at the bottom are all over the place, showing they're really poor predictors. So, to wrap things up, this work shows that grokking is a real and important phenomenon in large-scale LLM pretraining. It's not one single aha moment, but a series of local breakthroughs as the model learns different skills. And crucially, we now have a powerful new tool to see it happening. These pathway metrics, pathway distance and pathway consistency, provide a much more reliable signal of true generalization than training loss ever could. This offers a way to monitor learning without expensive testing. That's all for this week's AI Research Roundup. Thanks for listening.